Welcome, guys. So welcome to my GRE Math subject section. So we are solving 55. So 55 is a difficult question, which is it took me a while to think how to do this. So PQ are distinct primes. There are proper subgroup J. Basically, it's additive subgroup of integer Z. And ask you that J contains exactly three elements of a set like P plus Q P to Q to a P, and which three elements are in J? Okay, so everybody understand the question. Okay, so you say that so J is proper subgroup of integer and addition, and J contains some elements. Some three elements, which in this exactly three elements in the list, and I ask you about which one is possible. Okay. So the key idea is that this proper. So I need to mention some fact that you may forget. So the first fact is that Z is a principal ideal domain. Okay, or basically I can say that every subgroup, every additive subgroup in Z is just some integer A times Z. So basically what I'm saying that the only subgroup in Z is just like maybe there is the integer which is divisible by 2, or the integer divisible by 3, or the integer divisible by 4. Basically, this is all kind of the subgroup. Okay, and this also tell you that if Z, if any subgroup J contains two integers x and y, and the GCD of xy is 1. So that means if you have some integer, the subgroup J contains two integers, basically they're co-prime to each other, then J must be the whole Z, right? And this is due to the Euclidean. So Euclidean formula says that ax plus by equals to C has integer solution for any C if integer solution AB for any C if x and y are co-prime to each other. So basically, if you give me any positive any two integers and they are co-prime to each other, then basically you given any integer C, I can find A, B anyway to satisfy this equation. So due to this fact, then we can prove this, or basically you can use Z as a principal ideal domain, and you can prove this. Okay. So once you know these two keys, then you know how to do this. So the question is, now J is a proper in Z. So it means that J can only contains like, so that means J is J is a set of integers which is just divisible by some number, by some number. Okay, so once you have this basically basic fact, then we can start to solve this. So for example, if P is 2, Q is equals 3, then we can check that which one is possible. then we can get an answer. So A is the, maybe A has 6, P to the Q is 8, Q to the P is 9, and the B is 5, 6, and 8. C is 2, 5, 6. D is 2, 8, 9. E is 2, 6, 8. Okay. So basically, if J contains A, then 8 and 9 are co-prime to each other. So this will make J to be the Z. So this is what we don't want. Also, the 5 and 8 are co-prime to each other. So J is Z. Also, the 2 and 5 are co-prime to each other. So J is Z. Also, 2 and 9 are co-prime to each other. So J is Z. Only this one, right? So this one say that the 2, 6, 8 are basically the factor of P. The factor of 2. So now J is 2Z, which is definitely exactly the proper subgroup, the proper additive subgroup in a Z. So the answer is E. Okay, so once we done a special case, then you know how to solve it, because we contain P and Q, right? So for first one, if PQ and QP will not co-prime, and the second one, P plus Q and P plus Q and Q P to Q will not co-prime, and the third one, the P and P plus Q will not co-prime, and then the first one, the P and Q to P will not co-prime. So the only will co-prime. So the only remaining is E, that the P, PQ, and the P to Q, all of them are divisible by P. So E is what we want, because if this set contains two numbers which are co-prime to each other, then it will generate all the integer, then which is not a proper subgroup. So this problem is somehow difficult. If you remember Z is a principal ideal domain, then you can solve it quickly. But if you forget, then if you remember Z is principal ideal domain, you can solve it easy. And if not, then probably it's difficult for you to get an answer.